Venus is the closest planet to us in the solar system, yet paradoxically, we know inexcusably little about it. There is one key question concerning Venus to which we still do not have a clear answer. Is this planet alive or dead? Of course, we are not talking about biological life. We mean the planet's geological activity, and it is this very question that is linked to a curious paradox. When looking at the surface of Venus, one gets the impression that we are observing evidence of activity that took place at least in the relatively recent past. The face of Venus appears significantly younger than the surfaces of Mars or Mercury, and we don't have a complete understanding of why this is the case. It would seem that the most obvious thing to do is to draw a parallel with our own Earth, whose surface is also young and undergoes regular renewal. Such a comparison seems natural, especially if we consider the striking similarity in the basic characteristics of Venus and Earth, which, in theory, should lead to similar geological processes. But then we are forced to remember just how drastically the current conditions on Venus differ from those on Earth. Mechanisms that are fundamental to Earth, such as plate tectonics, appear to be absent on Venus. However, despite this, some process in the relatively recent geological past led to a complete transformation of the entire surface of the planet. Sometimes, the metaphor used to describe this event is that Venus turned itself inside out, and we still don't know the exact reason for this. However, there are some very plausible hypotheses, and the most intriguing part is that all the aspects I am touching upon now are closely intertwined. Today, we will talk in detail about Venus, about whether it can be considered alive, what evidence of its activity scientists are finding, what exactly constitutes the paradox of the young surface of the second planet, and how it managed to turn itself inside out. We will discuss the unusual and unparalleled features of Venus's relief and touch upon many other intriguing details. I must admit that I really enjoy preparing episodes that are entirely dedicated to a single specific celestial body. So I promise it will be extremely interesting. Why should we even ask the question of whether Venus is alive or dead, whether there is any activity there, and why study its geology at all? I suppose many of you have repeatedly encountered the following already cliché metaphor: Venus is the evil twin or evil sibling of Earth, and this definition contains at least part of the answer to our question. Yes, it is a twin because it is similar to Earth in many parameters, and it is evil because the conditions currently prevailing on its surface can only be described as hellish. The atmospheric pressure there is 92 times greater than Earth's. The average surface temperature is high enough to melt lead, and even significantly higher, over 460 degrees Celsius. Added to this are clouds of sulfuric acid and all the other delights. This we know well. But is Venus really that similar to Earth? Well, it all depends on what you compare it with. Our choice, frankly, is not particularly large. Although quite a few exoplanets have been discovered to date, we know very few details about them. So we are left to compare it with the other terrestrial planets in our solar system. Here they are, presented with their proportions preserved. And here are the basic parameters of all 4 planets. It is perfectly obvious that Venus is the closest planet to Earth in terms of size. The radius of Venus is 95% of Earth's radius. Consequently, both planets have a similar volume. The mass of Venus reaches approximately 82% of Earth's mass, and their densities are also close. For Earth, this figure is 5,513 kilograms per cubic meter, and for Venus, it is 5,243 kilograms per cubic meter. One might assume that all 4 terrestrial planets should have comparable densities. After all, it would seem they formed in the same part of the protoplanetary disk from the same building material. And if we look at Mercury, its average density is even closer to Earth's. But Mars, on the other hand, has an average density almost 1.5 times lower than Earth's. So we shouldn't take the close density for granted, considering the similar size and mass. It is on Venus that we find the surface gravity most similar to Earth's. Moreover, Venus, just like Earth, is located within the habitable zone of the solar system, or at least on its very edge. It depends on how exactly one defines the boundaries of this zone. In general, taking all of the above into account, Venus represents a very special interest for us. It is the only planet available to us for detailed study at close range that is maximally similar to Earth in its key physical parameters. We regularly hear news about the discovery of another exoplanet dubbed an Earth twin, but in fact, we know extremely little about these distant worlds. As a rule, our knowledge is limited to basic physical properties, such as size and mass, as well as the distance separating the planet from its star. However, studying our true twin, Venus, and understanding its evolutionary path can help us much better understand what conditions might be like on exoplanets and place these discoveries in the necessary context. I want to emphasize once again, Venus is the only twin of its kind, so close in its parameters, that is accessible for our study. There's a second important aspect. The study of Venus can help us gain a deeper understanding of our own planet as well. Again, this becomes possible through the analysis of similarities and at the same time stark modern differences. What exactly went wrong in Venus's history that it ultimately turned into this hellish world? In the context of exoplanet research, specialists talk not only about Earth twins, but also about Venus analogs. Within the general habitable zone, astronomers even distinguish separate so-called Venus zones. How often do planets falling into the Venus zone follow the same evolutionary path as our neighbor? How often do worlds formerly located in the habitable zone end up being completely unsuitable for life? Again, following the Venus scenario. In short, the study of Venus is of great interest and scientific importance. And besides the fact that this planet is interesting in itself, its research helps us better understand both Earth and those very exoplanets that we are discovering in ever-increasing numbers with each passing year. In many respects, Venus's transition to the dark side, its transformation into a hell uninhabitable for life, is due to processes in its atmosphere. And yet, the atmosphere is inextricably linked with geology. As an example, volcanic activity influences or has influenced in the past both the atmosphere and the planet's surface. And on Venus, this is especially pronounced. About some planets in the solar system, for example, Uranus and Neptune, we have very scarce knowledge for the simple reason that they are incredibly far away. They have been visited by only one single spacecraft, Voyager 2, and even that was just a flyby. And for now, all that remains for us, besides that data, is to study them using telescopes. Venus, however, is much closer than Uranus, and even more so than Neptune. The minimum distance to Uranus is 2.6 billion kilometers, while the minimum distance to Venus is only 24 million. On this illustration, of course, the scales of the distances are not observed, and it's impossible to show their relative positions in orbit. But in general, at the moment of closest approach, Venus is over 108 times closer to us. And spacecraft have, of course, visited Venus, not just once, but almost 50 times. True, not all of them reached it successfully. Here you see a list of all missions and flybys near Venus. Most of the early missions ended in failure, which, in general, is not surprising for that era. But afterward, many successful flights were accomplished. And spacecraft have, of course, visited Venus, not just once, but almost 50 times. True, not all of them reached it successfully. Here you see a list of all missions and flybys near Venus. Most of the early missions ended in failure, which in general is not surprising for that era. But afterward, many successful flights were accomplished. And yet, despite the planet's proximity and despite the considerable number of successful missions, we don't know nearly as much about Venus as we would like. And what hinders this is the exceptional difficulty of studying our neighbor in the solar system. This particularly applies to the aspects that interest us today, the geology and the surface of the planet. As we well know, the surface of Venus is completely hidden from direct observation in the visible range by its extremely dense atmosphere and continuous cloud cover. Even if we launch a spacecraft to Venus and it photographs it from a close orbit in normal visible light, this is all we will be able to see in the images. This doesn't give us much information about the planet's surface and geology, although, by the way, studying the atmosphere indirectly can tell us about this as well. But in any case, we would like to see the surface itself. And here, just as in the case of another celestial body, whose surface is hidden from us by an impenetrable atmosphere, Titan, we are forced to rely on two main methods: radar and infrared observations. Yes, at our disposal, of course, there are also images and measurements that were obtained directly from the planet's surface. In theory, such data could help us answer the question of whether Venus is alive and whether activity is observed there. But we still cannot give a confident answer to it, because we lack, for example, unambiguous and 100% proof of active volcanism that would be occurring right in our time. To be more precise, certain pieces of evidence, with varying degrees of confidence, do exist, and we will definitely talk about this more today. But what could be a more direct confirmation than a photograph taken from the surface, capturing a flowing lava stream or an erupting volcano? The only spacecraft that managed to photograph Venus directly from its surface are 4 Soviet probes: Venera 9, Venera 10, Venera 13, and Venera 14. They took images that were then assembled into panoramas. Here is the panorama compiled from the very first images, obtained in 1975 by the Venera 9 lander. This is the panorama from Venera 10. Venera 13 was able to transmit color images. Here are the panoramas captured by its rear camera and front camera. And these are the panoramas from Venera 14, composed of images taken in 1982. It's a great pity that there are so few images, but this is understandable, given that the landers operated on the surface for only 1 to 2 hours, and then, as was completely expected, they failed due to the severe conditions on the surface. And well, as we can see, no active lava flows are captured in these frames. However, this proves absolutely nothing, as we are talking about just 4 extremely short and localized observation points. Who knows, maybe right there, over the next hill, a volcano was erupting at that very moment. In short, in this situation, global scale observations would be very useful to us. And in this context, the main source of information for us is radar observations. What do we usually do when we need to photograph something, but the object is not well lit? Or in a situation where the room is pitch black and no amount of tweaking the camera settings will help? We take an external light source, like a lamp, or we simply use a flash. A radar, installed on a spacecraft, is very similar in its principle of operation to such a camera flash. It gives us the ability to obtain images of the surface. Even if it is completely unlit, the flash sends a pulse of light towards the object. The light that reflects off it returns to the lens and then hits the sensor or film. Darker, or conversely, lighter areas, areas of different shapes, surfaces at different angles, they all reflect light differently. And ultimately, the way the light has reflected allows us to reconstruct the image of the object itself. A radar, by and large, performs the same function. It is also based on electromagnetic radiation, just like a flash. The only difference is that this radiation has a different wavelength. Here we are dealing with radio waves, instead of visible light waves. The radar antenna sends a signal towards the surface and then registers the echo reflected from it. By full analogy with ordinary light, the way the radio waves reflect off the surface directly depends on its properties and its relief. And this is what allows us to obtain, or rather, reconstruct an image, measure the height of various relief sections, and even determine some physical properties of the surface. And most importantly, besides the fact that this method allows us not to rely on sunlight reflected from the surface, the key advantage of radio waves is their ability to pass unimpeded through the dense atmosphere and thick cloud cover of Venus. The first spacecraft to study Venus from orbit using radar was the NASA probe Pioneer Venus 1, which entered orbit around the planet in 1978. Over its 14 years of operation, it managed to map 90% of the planet's surface. This is what this map, based on radar images, looks like. The resolution, frankly, is pretty mediocre, about 10 kilometers. It couldn't distinguish details smaller than that. After it, there were other missions, but the best radar map of the planet that we have to this day was compiled thanks to the observations of the Magellan spacecraft. It studied Venus from 1990 to 1994. Thanks to Magellan, we have a map of 98% of Venus's surface, with a resolution of up to 100 meters per pixel. And on this map, we were able to see a great many interesting things. What immediately catches the eye when we look at the map of Venus's surface? You can ignore the color palette here. It's completely arbitrary. But if we take Mercury, Mars, Venus, and the Moon for comparison, and remove all the colors so they don't confuse us, we will still clearly see how drastically the surface of Venus differs from all these celestial bodies. I have intentionally excluded Earth from this comparison for now. We immediately notice signs indicating that the surface of Venus must be significantly younger than the surfaces of Mars, the Moon, and Mercury. This, in turn, already tells us that on Venus, at least in the past, some kind of activity took place that cardinally changed the entire planet. And this happened later than any activity on the other bodies with which we are currently making a comparison. So what are these signs of youth that we see? Well, I suppose many have already guessed what this is about. We have repeatedly discussed the age of the surfaces of various bodies in the solar system, and the most common examples of young surfaces we encounter are the surfaces of icy moons, such as Europa and Enceladus. In this context, I like to make a comparison, for example, between Europa and Saturn's moon Tethys. Both of these moons have an icy crust, but externally they are strikingly different. On Tethys, there is literally no untouched spot from impact craters. Here, everywhere we look, we see craters located inside other craters, which in turn are inside third ones. This is the most obvious and clear sign that the surface of this moon is very old. After all, according to modern scientific understanding, the vast majority of collisions took place in the early period of the solar system's existence, about 4 billion years ago. Celestial bodies fall and form craters today as well, but this happens much less frequently. Consequently, when we observe such a pockmarked surface, it becomes clear that almost nothing has happened to this body since the very moment of the moon's formation. The processes that are responsible for surface renewal on other bodies, tectonics, volcanism, or, in this specific case, cryovolcanism, erosion, and others, simply do not operate here. Activity as such is absent, and in the context of our topic today, we would be more likely to call such a body geologically dead rather than alive. And of course, what a striking contrast we see with Europa, on whose surface we observe many times fewer craters. This means that its surface has undergone renewal in the past, or possibly is even being renewed right now. Moreover, besides craters, we see many other intriguing formations there. All sorts of fractures, double ridges, and so on. All of this also serves as an indication of the presence of certain activity. As I already mentioned, asteroids have not stopped falling, they just do it much less often. Possessing knowledge about how many collisions, on average, occur over a given period of time, and by studying how the few craters that we do see are distributed across the surface, we can count how many of them have had time to accumulate. This, in turn, allows us to estimate the age of the surface. In short, regarding Europa, we can say with confidence that some activity took place there at least in the recent past, and it's quite possible it continues at the present time. and this is without a doubt a much more alive body than Tethys. For Europa, these signs of activity and the youth of its surface serve as one of the main arguments in favor of the hypothesis that a global ocean of liquid water is hidden beneath its icy crust. And now let's return to the inner solar system. Mercury. It is completely covered in craters. Externally, it is very reminiscent of Tethys, just like our moon. The moon, by the way, can be easily confused with Mercury by an uninformed person in some images. Here, try to guess. Which one here is Mercury, and which is the far side of the moon? Just so you know, Mercury is on the right. Mars, although its relief looks somewhat more diverse than Mercury's, also has a very old surface, which is pockmarked with millions of craters, much like the surfaces of the Moon and Mercury. But then there's Venus. Only about 1,000 craters are known on it. This is orders of magnitude less than on the bodies we just compared it with. Someone might assume that it's all about the atmosphere. Since it is many times denser than Earth's, it can probably serve as reliable protection against celestial bodies, which would simply burn up in this atmosphere. And the atmosphere certainly does have some effect, but no matter how dense it is only capable of stopping bodies up to a certain size. Larger objects, however, are quite capable of penetrating even such a dense atmosphere in one form or another. In short, the atmosphere alone cannot explain such a small number of impact craters. This means that something else is at play here. In the inner solar system, fewer craters are counted only on our very own home planet, Earth. Currently, only about 200 are known. So, the small number of craters can also be added to the list of similarities between Earth and Venus. However, the reasons for this similarity here, apparently, differ. What processes can destroy craters on Earth? Firstly, there is erosion. The action of wind and, more importantly, water can, over time, destroy the structure of a crater beyond all recognition. Secondly, there is volcanism. Large-scale lava flows can simply erase a crater from the face of the Earth. And of course, thirdly, plate tectonics. Thanks to decades of geological research, we know that the outer solid shell of our planet, the lithosphere, is not a single solid shell. Instead, it consists of individual lithospheric plates that are in constant independent motion. Primarily, these plates are set in motion by convection occurring in the mantle. Allow me to remind you that if we could take and teleport a piece of the mantle right here to us, it would look like a solid rock, just cooled. But this rock, nevertheless, is capable of moving, albeit very, very slowly. It is heated in the Earth's interior, near the core, and this hot material begins to rise closer to the crust. Then it cools, and the already cooled rock sinks back down into the depths. And this entire cycle repeats over and over. As I noted, this happens extremely slowly. Such cycles can take millions of years, and it is this movement of the mantle rock that forces the lithospheric plates, which are, so to speak, sitting on top of it, to move. At the boundaries of these plates, various situations can arise. There is spreading. This is the process where plates move apart. Such a phenomenon, for example, is observed on the ocean floor. In spreading zones, hot rock rises to the surface, which then cools, and this process forms a new, young oceanic crust. Consequently, on this new crust, there will be no craters yet. In subduction zones, on the contrary, one plate dives under another. And again, if there was a crater on the plate that is going down, we naturally will no longer see it on the surface. So, what from this entire list is present on Venus? Well, the answer is almost nothing. Firstly, erosion. The wind on Venus is indeed strong, but only in the upper layers of the atmosphere, at altitudes of tens of kilometers. However, directly at the surface, the wind speed is extremely low. Next, there is no liquid water on the surface of Venus at all. There are no flows that would be capable of destroying geological structures. No sediments or deposits are formed there. In short, erosional processes on Venus are extremely weak. and a crater that might have appeared, say, 500 million years ago, provided that nothing else has affected it, will be preserved in an almost unchanged state. Next, plate tectonics. Currently, according to all available data, it does not exist on Venus, and perhaps it never even existed there. Although this is not 100% certain, the planet's outer shell appears to be a single, solid piece. It turns out that craters on Venus cannot be erased in the same way they are on Earth, for example, through subduction. We are still left with volcanism. On Earth, volcanic activity is directly linked to plate tectonics, but this absolutely does not mean that volcanism cannot exist without it. Let's recall Io, Jupiter's moon. It is the most volcanically active body in the entire solar system, and as it is believed, there is no plate tectonics there in the form that it exists on Earth. But the volcanism there is driven by powerful tidal forces. Jupiter, in a way, squeezes Io and thereby heats its interior. And yet, on Venus, there are clear traces of volcanism. To put it mildly, about 75% of the entire planet's surface consists of lava plains. This means that the vast majority of the planet was covered in lava at one time or another, and we see the evidence of this right now. Science is aware of more than 200 large-scale lava fields, and in the data collected by the Magellan spacecraft, scientists found over 1,700 large volcanoes and thousands more smaller ones. The largest volcanoes reach a height of 9 kilometers from their base. This is, of course, less than Olympus Mons on Mars, but it is quite comparable to the terrestrial volcano Mauna Kea, if measured not from sea level, but from its very base on the ocean floor. But in terms of the area they occupy, Venusian volcanoes are indeed very large. Many of them exceed hundreds of kilometers in diameter, and the largest volcano, Sif Mons, reaches 500 kilometers in diameter. Many lava flows on Venus stretch for tens and even hundreds of kilometers. A whole range of volcanoes and volcanic features on Venus are very similar to those on Earth. However, others are absolutely unique to the second planet from the Sun. Differing from terrestrial analogues, for example, are the so-called flat-top domes. This is what they look like in radar images. They are called pancake domes. Well, they really do look like pancakes. They are formed when particularly thick, viscous lava emerges onto the surface and then spreads out evenly across the surrounding terrain, like pancake batter on a griddle. Another set of interesting features are the coronae. They can form when magma rises from the interior but doesn't reach the very surface, and its uplift causes the formation of these circular bulges. There are also so-called arachnoids, which externally resemble spider webs. These formations, with a high degree of probability, are of volcanic origin and have been found only on Venus. Or, for example, novae. They should not be confused with stellar flares, supernovae. The main conclusion we can draw is that volcanism played a colossal role in shaping the surface of Venus that we observe today. And by all appearances, it is precisely volcanism that is responsible for the rejuvenation of the planet's surface and for the fact that there are so few impact craters on it today. This leads to two subsequent important questions. In what exact way was this volcanism able to rejuvenate the entire surface of the planet? And is it still ongoing? What is so strange about Venus's volcanism? Well, for example, the sheer quantity, variety, and gigantic size of the volcanic features clearly indicate that for them to have formed, there must have existed numerous giant magma plumes, or magma reservoirs, beneath Venus's crust. Why are there so many of them on Venus? How did such huge reservoirs of magma manage to accumulate? We don't have the answers to these questions. Another question arises. I have already mentioned that on Earth, volcanism is closely linked to plate tectonics, and on our planet, volcanoes are, as a rule, concentrated in specific, defined areas at the boundaries of lithospheric plates. On Venus, however, as we have already found out, there are no separate lithospheric plates. Yet the volcanoes and other volcanic features are distributed relatively uniformly across the entire planet. Here is a map showing their distribution. How could this have happened? And what mechanism controlled this volcanism if plate tectonics was not involved? Scientists identify two main plausible scenarios for how the entire surface of Venus could have undergone renewal, erasing all the old craters and other relief features. The first option is a catastrophic resurfacing of the surface. That is, in a relatively short period of time, perhaps on the scale of just tens of thousands of years, the entire planet, figuratively speaking, turned itself inside out. This was a single, global volcanic event during which lava poured out onto the surface absolutely everywhere across the planet. The second option, a more conservative one, suggests a gradual resurfacing of the surface. According to it, everything did not happen almost simultaneously and everywhere, but was stretched out over tens or even hundreds of millions of years, during which numerous local events occurred. Individual eruptions gradually renewed the surface. Both Earth and Venus have very hot interiors and molten cores. This internal heat has two main sources. Firstly, it is the heat left over from the time of the planet's formation. The second source is the decay of radioactive elements in the interior. In short, the planet is gradually cooling, radioactive elements are decaying, and all this heat needs to go somewhere. On Earth, hot rock has a way to reach the surface thanks to the mechanism of plate tectonics. The heat has an escape route. But what happens if there is no plate tectonics? What then? If heat is being generated, but there is no way out for it, it will begin to accumulate. As a result, the mantle starts to overheat and melt. At a certain point, vast sections of the mantle can melt, and as a result, colossal magma reservoirs are formed. From there, the situation can reach a critical point. The crust will no longer be able to contain all this accumulated heat, and a global eruption occurs across the entire planet in a geologically short period of time. This event ultimately leads to a cardinal transformation of the entire planet's surface, erasing old craters and other features from it. What I have just described is the catastrophic scenario. Various models and scenarios exist that may differ in their details, but in broad strokes, their essence is roughly this. After the completion of the global catastrophic volcanic event, when the planet has finally released all its excess heat, all processes return to a relative norm, and for some time, nothing extraordinary happens. It is quite possible that there were several such events in Venus's geological history. Just imagine if someone lived on Venus. They're just sitting there, not bothering anyone. And then suddenly, boom, volcanoes start to activate all over the planet, completely reshaping the surface. As for the gradual model, it can be realized under the condition that Venus's internal structure is more similar to Earth's. In this case, volcanism arises gradually, in random places, and renews the planet's surface at a much slower pace. We do not know what actually happened. Models based on both the first and the second scenario are equally capable of reproducing the surface picture that we observe on the planet today. Naturally, Venus's internal heat supply is not infinite. It's Io that is constantly being heated by external tidal interactions. But Venus does not have such a mechanism. This means that if we assume that the catastrophic scenario with repeating cycles is what's happening there, then sooner or later, the planet will cool down inside sufficiently, and the next event of global volcanism will be the last. And this is where the key question arises. Wasn't the very event that created the current appearance of the surface, in fact, that last one? We, again, do not know. But this brings us very close to the question of what is happening on Venus right now, and whether any activity has been preserved there. Crater counting and analyzing their state of preservation allow for an approximate estimation of the age of Venus's modern surface. In scientific literature, one can find estimates of 300 to 600 million years, as well as a wider range, from 150 million to 1 billion years. If we take the minimum estimate of 150 million years as a basis, then by geological standards, considering that the planet's age exceeds 4.5 billion years, this is very recent. If the surface renewal process concluded back then, perhaps we are now observing a quiet period of stagnation. Or this was, in principle, the very last renewal, and the planet has geologically died. Targeted studies of the modern surface and the search for traces of activity that could be happening right now could help us answer whether this is the case. As I said at the very beginning, the direct discovery of active lava flows would be an extremely strong argument, but we haven't had any such findings yet. However, even without this, many interesting discoveries have been made. Besides radio waves, infrared radiation is also capable of penetrating through Venus's cloud cover. But in this case, we are no longer relying on waves reflected from the surface that we send ourselves, as in radar, but on the intrinsic thermal radiation that emanates from the surface itself. With a certain effort in the infrared range, one can even distinguish some global relief features, as for example in these frames. They were obtained during a flyby of Venus by the Parker Solar Probe in 2021. The captured geological features matched exactly what we had previously seen on radar maps. The European spacecraft Venus Express also studied Venus in the infrared range. Based on the character of this infrared radiation, it is possible to estimate the approximate age of a particular surface area. Thus, the age of some solidified lava flows near volcanoes was estimated to be in the range of 2.5 million to just a few 100,000 years. If the latter, lower estimate is correct, it turns out that eruptions and geological activity were occurring on Venus just yesterday. Another study, which also argues in favor of recent activity on Venus, took a different path. In that work, the authors focused on studying the relief features already mentioned today, the coronae. They first modeled their evolution and estimated what these structures should look like at different stages of their development, and then they compared the results of this modeling with actual radar images of these formations. And the authors of this study concluded that at least 37 coronae have been geologically active very recently. The authors of another study analyzed radar images obtained by the Magellan spacecraft and discovered sections on the surface that looked like separate fragments or blocks. They also found traces that these blocks had been in motion in the relatively recent past, which also serves as an indication of recent activity. If we are unable to catch a lava flow directly in action, then maybe we should try to find traces of what it has done. To do this, one needs to find observations of the exact same surface area that were made at different times, and then check if any changes have occurred in the more recent image compared to the older one. Magellan observed Venus for 4 years. It was quite possible to try to find something like this. And scientists found it. A sensational article was published about this in 2023. Here we see radar images of the exact same location. And by all appearances, they clearly show changes in what looks like a solidified, fresh lava flow. This perhaps is one of the most direct confirmations of the presence of activity on Venus out of all those that are available to us at the moment. The only thing is that we should not completely rule out the possibility that we are dealing with some kind of error or artifact in the data, but the scientists themselves are quite confident in their conclusions. Last year, an article was published that used a similar approach, and in it, within the same Magellan radar data, signs of surface changes were found in 2 other regions as well. And this means that volcanoes could very well have been erupting on Venus in the period between 1990 and 1992. And this, of course, is not all. In short, the use of different methods and the analysis of a large volume of data indicate that even if there is no global activity on Venus, some kind of local activity was present there very recently. And considering the data dating back to the 90s, one can generally assume that it is happening right now. By the way, studies of the atmosphere also point to this. In particular, the detection of certain substances in it that are directly related to volcanic activity. There is another interesting study that puts forward the hypothesis that convection on Venus may be occurring not in the mantle, but directly within the planet's crust itself, which also undoubtedly is a form of certain activity that influences what we see on the surface. In general, it is highly probable that Venus is not dead after all. This, of course, doesn't make it any easier for us, in the sense that we are unlikely to be able to hang out on its surface. The only remaining option is perhaps to fly in airships at an altitude of several tens of kilometers, where the conditions, as is known, are quite comparable to those on Earth. The problem here, however, lies in the fact that the main body of data we have been discussing today is already quite old. The Venus Express mission ended almost 20 years ago, and Magellan a full 30 years ago, and that is why scientists are now placing enormous hopes on two planned missions, Da Vinci and Veritas. The Da Vinci mission will consist of an orbiter, whose task will be to study the planet at different wavelengths, as well as a descent probe, which will study the planet's atmosphere while being directly inside it. And the Veritas spacecraft is set to finally compile a completely new radar map of the planet and obtain radar images with a resolution that will be orders of magnitude superior to what Magellan gave us. Both of these missions have the potential to significantly expand our knowledge about our closest neighbor in the solar system. The only pity is that we will have to wait a long time for their launch. If there are no delays, and certainly no cancellations, then they should set off for Venus in the early 2030s. An entry into orbit around Venus will accordingly take place closer to the mid-2030s. Well, what can we do? We will wait. The main thing is that these missions are not cancelled, because nowadays, unfortunately, that happens easily.